Up until this point, we've been looking at two-dimensional Cartesian vectors, and we know that a 2D vector is nothing more than a directed line segment. It is a direction and a length, and our 2D vectors have been encoded with an x component and a y component. So we have an x and y Cartesian component, and they give us both a direction and a magnitude, a length of that directed line segment. Well, from this point onwards, I want us to start looking at three-dimensional Cartesian vectors. So what would a 3D vector consist of? Well, it's no different to our 2D vector. It's still just a directed line segment. It is a direction and a magnitude, a direction and a length. Except our 3D vector, quite logically, exists in three-dimensional Cartesian space. Now, as most of our work in computer graphics and graphics-related programming exists in 3D space, it makes sense that 3D vectors are going to be incredibly useful to us. So because these vectors exist in 3D space, a 3D Cartesian vector is going to have not only how far do we travel in x and how far do we travel in y as its components, but it's going to have how far do we travel in x, how far do we travel in y, and how far do we travel in that third dimension, how far do we travel in z. So a 3D vector, if we have our 3D Cartesian space, so let's say that was our y-axis, I'm going to scroll down, there we go, this is our x-axis, say, and this would be our z-axis, so y, x, and z. A 3D vector is going to tell us how far do we travel in x, how far do we travel in y, and how far do we travel in z, and it's going to give us some directed line segment that exists in three-dimensional space. So logically, if a 2D vector tells us how far we travel in x and how far we travel in y, the only difference with a 3D vector is that it's going to have a third component. Instead of just x and y, we're going to have a z component. So our 2D Cartesian vectors have two components, an x and a y component. Our 3D Cartesian vector simply has an additional component that deals with how far is that vector travelling in z. So really there's nothing to our 3D vectors. We can have a look at a few example vectors, but there's really nothing to them. They're very simple. So if I clear some space on our axes, and to save me from having to erase things over and over again, in a second I guess we can draw these on a new layer, but I will add some units to our axes. So let's say this is 1, 2, and 3 in x, 1, 2, and 3 in y, and 1, 2, 3 in z. Now obviously I'm dealing with a two-dimensional whiteboard, so it's going to be a little hard to see this, but if we had a vector and that vector v was equal to, I don't know, 2, 1, and 3. Fantastic. So what this vector is telling us is that we're travelling 2 units in the x-axis. So let's say that it was starting at the origin. Again, this is an arbitrary choice because just like our 2D vectors, our 3D vectors are free to float around our Cartesian space. They don't exist in any particular location. They simply have a direction and a magnitude. But if we started this at the origin, we know we're travelling 2 units in x. So we're travelling 2 units in x. We're travelling 1 unit in y. So 1 unit in y. And then we're travelling 3 units in z. So we're going to be travelling 3 units in the direction of our z-axis, which we could perhaps show something like this, maybe helps visualize what's going on here. So we're travelling 2 units in x, 1 unit in y, and 3 units in z, which means we're going to have a vector that looks something like this. Now obviously again we're dealing with a 2D whiteboard, but hopefully you can conceptualize that this is a line segment that exists in 3D space, and the components of this vector are simply telling us how far we travel in x, how far we travel in y, and then because we're dealing with 3D, how far we travel in z. So I'm going to introduce just one more example, and in this case let's have another vector. And in this case, I don't know, let's go with 1 unit in x, 2 units in y, and minus 3 units in z, for example. So our z-axis, obviously it continues in the negative direction, so minus 1, minus 2, minus 3. So in this case, again, I'm going to start as at the origin, just for arbitrary decision. So we're travelling 1 unit in x, so 1 unit in x. We're travelling 2 units in y, and we're travelling a negative 3 units in z. So we'll be travelling negative 3 units in z. So something like this might help us visualize what's going on here. So we're travelling 1 unit in x, 2 units in y, and negative 3 units in z. And we're going to get a vector that looks something like this. So this would be our vector v. You'll notice our notation is pretty much identical. The only difference is we have an additional component. So again, we could have a variable that has a bold name. We could have a variable that has a line above it, or a variable that has a small arrow above it. In either case, it just means that we have a vector. There's no difference in the way that we note that we have a vector in 3D or 2D. You'll notice again, all of our components are included inside of square brackets. In this case, I'm dealing with a column vector, but this could have been written as a row vector. So again, just like the 2D case, we can have column vectors, we can have row vectors. There is no real difference. The only difference is we've introduced a third component, and the reason we need to introduce that component quite logically is because in 3D we need to tell the vector, if you will, how far we're traveling in this new z axis, which we didn't have before when we were dealing with 2D. So that's really simple, and because it's so simple, I'm not going to set any questions here. Now, over the next few videos, what we're going to do is we're going to recap everything we've seen so far with 2D vectors, but we're going to apply those concepts to 3D vectors. This is going to act more as practice than anything, because the theories are very simple once you've understood the 2D case. But I do want to introduce them in the 3D case, and also just give us some practice working with vectors and working with different operations that we can apply to vectors. Once we've covered everything that we've already covered, but for 3D, we're then going to move on to explore some more advanced topics as they relate to 3D vectors. And that's when the real power of vectors is going to become quite apparent, I hope. But that is going to conclude this video, and these next few videos are probably going to be quite short because there's nothing to 3D vectors. They're simply an extension of the 2D case. We simply have an additional component. And as long as you understand that we have a component that tells us how far we're traveling in x, a component that tells us how far we're traveling in y, and the only difference is we now have a component that tells us how far we're traveling in z, then you're going to have no issues dealing with 3D vectors. So that is going to conclude this video. Thanks a lot for watching, everyone.